lost about everything. Everything is great. Okay.
84 effort.
Sorry.
All good, all good.
Oh, good.
Yeah.
Thank you. Yeah, great. Let's spin in quantum mechanics now. Okay, so let's do something fun. We've been learning about the formalism of quantum mechanics. We have uncovered, or we have analyzed two different setups. One was the interferometer, and the other one was the polarizer. And we found out that we could predict some outcomes from them. And okay, so then we just describe the system. You answer some questions on the test. But maybe you can ask this question, which is, what can we use quantum mechanics for? And the reason why I want to go through this is because there is a big revolutionary change today, or there's a large driving force towards building quantum technologies. And a lot of that is spurred by answering the question, how can we harness the power of quantum mechanics? And how can it be useful in our everyday lives? At the very beginning of this lecture, of this class, I told you that we use quantum effects in our everyday lives, like lasers, semiconductors, MRIs, for example. I would call them, or people call them, the first quantum revolution. So we are using quantum effects, but we are just using them in a very macroscopic fashion. Now we are in this age where we're trying to use them in a second quantum revolution, where we're trying to process information using them. We're trying to do fine-grained calculations using them. And this is the driving force behind quantum computers, quantum algorithms. And today, so obviously you don't have the background to understand full-blown quantum algorithm yet, but I want to give you a flavor as to how it can be useful in at least one toy context. Treat it as a baby example and treat it as more of a proof of principle, fun topic, not very practical, but still it illustrates how it can be useful. Okay, so this goes under the name of the Elitzer Feynman bomb test. This was in 1993. I believe that if you go look it up online, you can look up the original paper and read it. It should be pretty accessible by now. And I do not know what the context that this paper was written in. Perhaps these two guys were having coffee at a cafe and said, what good is quantum mechanics? Let's just write some paper about some toy problem they can solve. Maybe they're having a beer or whatever it is. So the whole point of what I'm trying to say is that ideas like this come about very spontaneously. Like you're just having a chat with your friend about what can we use it for. Let's think about that, and then they write paper. So this is what I do at conferences, for example. I hang out with people and just talk to them. Okay, so these people are asking the question, okay, what good is quantum mechanics? Besides just a description of reality, they ask this question, hypothetical question. They imagine this. Let's suppose that you have a factory which is producing bombs, and the bombs, let me denote them by this. Bomb is activated by sending in light through this people. So light. If we send in light, if light is sent in, boom. Okay, so it explodes. Now the trouble with this factory, where the bomb is being created in, is that it's not very good. Sometimes it produces defective bombs. Sometimes it produces working bombs. So the factory produces working and defective bombs. Okay, with this in mind, this setup in mind, let me ask you this question. Suppose that someone gave you a batch of bombs and said, I would like to verify that they are working, that they are operational. How will you do it? So just think of any possible solution. Like, so what I'm asking you to do is think of an algorithm on how to answer this question. Is it working or is it effective? Now, because the bomb is activated by light, obviously a way of testing whether it works is to send in the light. But if I send in the light, then the bomb explodes and I don't have a bomb anymore, or worse, I don't have my cell phone anymore. So this is a solution, but not a very good solution. Okay, so you've used up the bomb in the process of testing it. What we see is that classically, and this is an example of a classical algorithm, which is if I send in a light, I can definitely verify if it is working or not. But I have used up the bomb. So that's no good, right? I ordered a bunch of bombs, I want to use it. I want to verify that it's working. Then I verified them, I have no more bombs left. Okay, not great. So Elizabeth and Wyman said, perhaps there's a way to verify that the bomb is working without blowing it up. At the surface level, how is it possible? Think about it. You use your imagination. The bomb needs to be, like, when you receive it, you wouldn't know if it's working or not. To test it, obviously you have something like, how can you verify that it is working, but at the same time, not detonate it? Okay, I'm also assuming that we cannot dismantle the bomb. We cannot open it up. All we can do is just either set in a light or not set in a light. Okay? So imagine, complicated question, right? Okay, quantum mechanically, there's a solution. So let's erase this. So they said, let's say Wyman said, stick it into a Mach-Zehnder interferometer. So here's what they imagined. Again, let's have our setup. You have two halves where the light would exist, either the top half or the bottom half. Let's suppose that we set in light in the top half. And then it goes down. It gets split into two parts according to a beam splitter. So part of it gets reflected, part of it gets transmitted. Then there's a mirror in which we're going to bounce the beams off it. Okay, so the mirror again is not going to do anything except for us to allow us to interfere the beams again. And then we're going to interfere at a second beam splitter. And then we're going to detect them. So here there's no phase shift, it's just like two beam splitters, right? So here's mirror, mirror, blah, blah, blah. Okay, so where should we stick in the bomb? So Elizabeth Wyman said, well, this, we can either do it in the top half or the bottom half. But let's imagine that we stick it in here. Suppose that we design this apparatus, and there's a way to put in the bomb there. And put in the bomb here. Okay, so let's set some terminology. If it's effective, I call it a dud. If it's working, I call it live. Okay, so it's just like words. Okay, so let's see what happens. Let's do the easy case first, and okay, before that, let's also model the beam splitters. So we model that in the midterms and also in the class before that as a ferret imagine that we model the beam splitter according to this picture. Just set things correct. Okay, a bit different from what you're used to in what you've seen in your midterms, but okay, let's verify that it is unitary. Before that, let me just ask a quick fire question. If I write down this matrix, what is its action on an up state? So if I ask you to calculate Bs acting on up, what does it do? Anyone? Come on, let's not get stuck here. Let's get to the fun part. Yeah, so 1 over square root of I over square root 2 up, plus 1 over square root 2 down. Right? Don't forget that when you read the action of the matrix, like you're just reading off this code, right? So you have I on 1. And then similarly, if you do Bs on down, you should get 1 over square root 2
the other side.
up plus I over square root 2 down. And let's verify that this is unitary. So yes, there you go.
Yeah.
It's 1 over square root 2.
Negative I.
Let's do minus I.
1, negative
minus I. And so if we do Bs diagonal Bs, that's equals to 1 over square root 2, 1 over square root 2 times minus I, 1, 1 minus I,
1, 1, I.
1, I. And that's equals to 1 half, blah, 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 2,
2, 0, 0, 2.
blah, 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 0, 0, 2.
Identity.
And that's the identity.
Yeah.
And so it is indeed unitary. Okay, very good. So that's a valid choice of a beam splitter. If I give this recipe or this request to someone in the lab, they can create a beam splitter that has these characteristics. So someone's able to make this. Okay, so let's ignore this. That's just to verify that we have not violated any physical principle. Okay. Good. So let's assume that somehow the bomb is a dot. So let's calculate what happens. Case dot. Okay, if it's a dot, then essentially the bomb minus going up in there. What's happening is that the light passes through, it doesn't get absorbed by the bomb, and then it carries on through, so just ignore the bomb. So then we can ask the question, what do we detect at the end of it? What do we detect? So just before the detector, the state of one photon has passed through 2 beam splitters, right? So by Bs one time and Bs second time. Right? There's no phase shift, right? It's just light, initial state, undergoes a unitary transformation once, reflects, undergoes a second unitary transformation, and then we detect it. So this is just before the detection. So let's do the calculation. So easiest thing to do is in matrix form. So let's do 1 over square root 2 times, what's it again? I, 1, 1, I, 1 over square root 2, I, 1, 1, I, acting on 1, 0. That's equals to 1 half, I, 1, 1, I. And then when I apply the column vector 1, 0 onto this matrix, I'm taking out the first column.
I1.
therefore, the answer is that just before detection, the state is I times of now. Okay? That's just math, right? Like, don't get stuck on this. Okay, good. So now we can start to list down events that could happen. That happen in the case when there's a dud. So let's first tabulate the probability that the bomb explodes is of course 0, because this was a dud. Now, what's the probability that the detector sees up? Okay, so this was a state just before detection. So we can do the calculation. The probability of detecting up is equal to the projection of my waveform, this positive state
One beer.
in the up state. Because don't forget, this detector is modeled by up, up, minus down, down, which you already see without any calculations, hopefully, for all of you. This is already in the spectral decomposition with eigenvalues plus 1 and minus 1. So when we measure this operator, which is emission, we see the outcomes plus 1 and minus 1, and we see them with probabilities given by how much weight it is here versus how much weight it is here. So what I'm calculating is how much weight it is in the up state. So this projector on the up is just the outer point of up and up. And if I do the calculation with knowledge that my wave function is I times of down, then you can see this is 0. Okay, because the state is not up, right, clearly. And therefore it means that projector onto the, the probability of the detector seeing down is 1. Okay, so let's tabulate this. 0, 0, P of the down is 1. Good. Okay, what have we learned? We learned that the bomb is not there. Obviously, the bomb doesn't explode. The bomb is the dot. Obviously, it doesn't explode. And moreover, when we send in the light through the interferometer, we always see it appearing down. So the light goes from here, scatters 100%. Okay. Now let's switch cases. Let me raise this calculation. And let's try to write this here. Case alive. Case live. Okay. So if the bomb is indeed a live bomb, what's it going to do? If the light has been sent into it, it will explode, and then the experiment just stops, right? You don't have to do any more calculations because you're not there anymore, right? Okay. Then, what happens? Okay, so how should we model the bomb? What the bomb is that it itself acts like a detector. It detects down. If it detects down, it explodes. If it doesn't detect, then by the bond rule, it means that you have collapsed the photon on the up branch. bomb itself as a Hermitian operator, which has eigenspectrum down and up. And all I'm just trying to say is that you associate the detection of the down state with the event of explosion afterwards, because that's what the bomb does. And if it detects the converse, which in this case means it doesn't detect, then you would have collapse by the bomb onto the up branch, right? Okay, are we okay with this? Okay, so now we can split the cases up. First, let's do the calculation. What's the state just before it enters the bomb? Like here. What side just before bomb? So again, it is just Bs acting on up, which, okay, I've written it down here. I over square root 2 up plus 1 over square root 2 down. Okay, so this is this spot here. If you want, I can say, let's call it 1. 1. Okay, now we can ask, what's the probability that the bomb explodes? Now, there is some component of a light in the down branch. So let's calculate how probable is it to be the down branch. And that's given by this state of psi of 1 in the down branch. Oops. And, okay, do the calculation. We get P is the down projector. We select out this component, 1 over square root 2. Then, okay, so let me work it out in full. P acting on down is 1 over square root 2 down. And then we multiply that by psi I. But psi of I only has one component, like this component is down, only this one survives. So there's 1 over square root 2 times 1 over square root 2, and there's 1 up. Agreed? Okay. So let me calculate this. K starts this way. And let me calculate it here. K is alive. P of the bomb explodes equals 1 half. Okay, let's continue. Good. Okay, so if it explodes, then our lab is destroyed at the stop. But what happens if it does not explode? It means that it has detected it in the up state. So if bomb did not explode, by the bond rule, the bond update, can you see? The new state, psi, after bomb, has been projected into the up state, psi, up before bomb. So let's call this 2. So psi of 2, this one is 2, is equals to the projector onto the side, the up onto the side of 1, divided by the square root of psi p up psi Now, projecting on the up just gives me this term, right? I over square root 2. Then, you can ask, how much, what's the probability of detecting up? If you do this calculation, it's just 1/2. So you know the square root is 1 over square root 2. So it's I over square root 2 divided by 1 over square root 2, and it's just I. I times a half. Do you agree with that? I mean, as it should be, right? Because like even without doing the calculations, if you see that your state is up, it must be up. So here we have I times of up. I'm being very fastidious here and keeping the I. The I is a global phase, so you can ignore it. But let's just keep it for now, right? Just not to confuse you guys. Okay, we're almost there. This is 2. This is 1. So we know now that at 2, if the bomb is live, it's purely an up. So it's only coming down here. Last step. What is psi at 3? Just before the detector. Okay, so let's write it here. So, question. What is psi just before the last factor? So let's call it 3. And that is Vs acting on I times R. Okay, and then you do the calculation. That is 1 over square root 2 times I 1 I times I 0. Because this term is this vector is I 0. And then some math. What we get is what happens? I 1. Good. So therefore, this is I over square root 2 up plus 1 over square root 2 down.
Hold on.
Okay? I should really add the condition. This is conditioned
Yeah.
upon bomb not exploding.
Prof. Isn't it supposed to be 1 over square root 2 negative 1, 1? Because it's I times I.
Oh yeah, you're right.
Yeah.
Sorry. I'll do that. I minus 1. Right?
Yeah.
Okay. Good point. Okay, so now we can ask the next question. What's the probability that my detector sees up given that my bomb did not explode? So that's the state just before detection. So again, I have to do psi p of up, psi of the third state. And, okay, that's minus 1 over square root 2 squared. This one up. Yes, are we all following?
Yeah.
Do we have to, I mean, like, look at the state, it's equal weight. So I trust you can do you can connect the dots. Okay? I appreciate the story, because if you're not following the map, then unfortunately, yeah, that's unfortunate. Okay. Similarly, P of detector seeing down, given that the bomb did not explode. This equals to psi of 3 P of down psi of 3 is equal to 1 half. Great. So naturally, if you ignore this part of the diagram, if you knew that your light is coming in as an up state, then you get a 1/2 chance of seeing up, 1/2 chance of seeing down, as it should be because the beam splitter is a pair of one. Okay? But then let's ask the question, how often did the bomb not explode? What's the probability of the bomb not exploding?
1/2.
1/2, right? How do we get that? Because if the bomb explodes, it's 1/2. So the converse of that bomb explodes is 1/2. Therefore, we can put it all together, and we can find out that the probability of the detector seeing up is the product of how often the bomb did not explode times, given that the bomb did not explode,
Up.
you see up. Okay? This is nothing more than just Bayes' rule, conditional probability. I remark, for those of you who have not seen this, if you have two events, or two random variables, let's call them x and y, the probability of x comma y is given by the probability of x and y is equal to the x given y times how often y appears. Okay? If you've not seen this, then you must see it at some point in your education, in US education. Because you cannot leave university without seeing it. Okay? Right? You've seen it here, right, sometimes. But it makes a lot of intuitive sense. I mean, like even without the formal map, it's like saying, right, of course, I need to ensure that the bomb did not explode first. Then I can talk about how often my bomb how often my detector sees up, given that my bomb can explode. No, that makes perfect sense, right? Like you condition it on that event happening. And so this is 1/2 times 1/2 from those two numbers over there. And this is 1/4. Similarly, probability of detector seeing down is probability of detector seeing down, given that bomb
This one explode.
did not explode,
E did not explode.
times how often bomb did not explode. And that is 1/2 times 1/2, is just 1/4. And let's box it up. So let's circle the relevant numbers. Bomb explodes 1/2 of the time. Bomb explodes 1/4 of the time. Sorry, the detector sees it up 1/4 of the time. Detector sees it down 1/4 of the time. Thankfully, everything adds up to 1. So our theory is still consistent. If some numbers are up to 1, then something is wrong with calculations. Okay, so we've accounted for all the events that could happen. And that's the end of the story, right? Look at what's happened. There was not any hard mathematics at all. There was no algebraic topology, there was no analysis, there was no epsilon and delta. It was just basic matrix multiplication, 2x2 matrices, and just using quantum mechanical models, just a story that says that you should use one update. Then we just track how things happen. But then now let's give a physical interpretation of this. Sorry, not physical interpretation. Let's understand what we have done and how have we solved the original question of detection without blowing up. Look at what's happened. Here in the case when it's died, you never see the bomb explode, you never see it up. So if you run an experiment, and you see, and your detector detects up, then you can conclude this thing. The bomb is working. Because if the bomb were not be working, you never see it up. So you have concluded that the bomb is working, but you have not exploded the bomb. You have not detonated the bomb. Isn't this like remarkable? You have managed to verify it without using the equipment, despite the equipment, needing a light to activate it. Okay, this is a remarkable magic, so you will, of non-local nature of quantum mechanics, of linear superposition, right? So what else can we conclude? If we see, in the event that the detector sees down, then we cannot conclude. It's inconclusive because it could have come from a dot or it could have come from a line. But that's fine. Just run the experiment again. And then if you see it up, okay, then you know that it's working.
What is a 50%
But of
chance?
course, there's a chance that you destroy the cell.
Yay.
So it's not a very, you probably wouldn't sell it to an investor. Say that I create a tester and half of the time, you would not
Kaboom.
make it up. But hey, 1/4 of the time you work it up. You make it up. But still, this already signifies that you can, in principle, verify some cases without exploding. Okay, this is not possible. This is already one example of a quantum advantage. This is why it's known as a quantum advantage. Of course, more practically, in everyday matters, we, of course, are not trying to make a bomb tester, but we are trying to, for example, run an algorithm to factorize numbers, and the basic idea is more or less the same. We're just trying to ensure that some events happen quantum mechanically either more often or in fact sometimes it even happens more than classically more than a classical algorithm would perform. Okay, so this is a powerful quantum device. Any questions here conceptually? Okay, I'd like you to pause and let this sink in. And everyone following the logic, right? If we see up, we are for sure knowing that the bomb isn't alive, because the case when the bomb is alive will never ping up.
So this is detecting it without using the bomb in the first place. It's assuming that there is like a bomb that acting as a detector.
Yes, you're right in that the bomb has not been used up, in the sense that it is not detonated, but its effects are there, right? Without it being there, you will never see it being up. Crazy, right? So its presence, despite not being used up, has altered the outcomes, the physical realities, in such a way that you can use it to your advantage. Okay, so then I threw it on this challenge to you guys. Now that you've learned the basic rules of quantum mechanics, you can start to invent by yourself, go home at night, on the toilet bowl, whatever it is. Think about which algorithms could benefit from quantum mechanics. Can I stick it into an interferometer? Can I use, let me tell you honestly, the rules I taught you, the basic rules of quantum mechanics, that's all that is. Okay? I should clarify that. It's not all that is in the sense that there's a lot of physical intuition to build up, but if you strip it down to its core, everything is based on those rules. And so in principle, you should be able to develop new algorithms based on such ideas. Okay? Just need some thinking, some ingenuity, some creativity, some discussion with friends, a little bit of coffee, question to ask is, hey, the bomb explodes one half of the time. How can I improve it? Can I modify the setup algorithm so that I blow up myself less, yet I can still detect it? Ideally, I want this event to go to 0. I want this event to go as large as possible. I want this to go to 0. Why? Because I don't want inconclusive cases. Neither do I want detonated cases. But I want, a case where I can positively identify it and yet not blow up. So how do we do that? How should we change it?
Try to make it split in a way that it goes, most of it goes to the top part.
Okay, so you want to change the beam splitter in such a way that, say, like 99% goes up here and 1% goes up here. Yeah, okay, that's great. Okay, but even without doing the math, right? Let's think about what happens. If only 1% say that like 99% goes up here, right? Then the bomb explodes very rarely. That's true. So your rate is very, very, good. But at the same time, you have most of the light is now in the half state, and so when you undergo a beam splitter, it's 1/2, 1/2. Okay, so indeed, the probability of the detector seeing up is 1/2 times a large number, like 99%. So yes, you've helped it 1/2, 1/2. Great, good. So that's one possible improvement. So presumably your classmate has already stumbled upon one great improvement. She has made the bomb not explode by making the beam splitter, say the first one only, not the second one. The first one, make it a very non-transmissive beam splitter. So most of it goes down. Most of it goes up. Very little of it goes down. If that's so, then this triggers very rarely. And then essentially what's happening is that you have just a light that is. Oh, no, but hang on. Let's be careful. This will also modify this calculation, right? Okay, so this solution does not work. Because if most of the light was transmitted here anyway, then the case when it's done, that's essentially the same as not having the bomb there. So then you'll get 1/2 here and 1/2 here. Roughly speaking, or 1/2 here, 1/2 here. And you'll also get 1/2 here, 1/2 here. So you make your distinguishability worse. You have reduced the chance of the bomb exploding, but then comparing the case when it's done versus live, you cannot tell them apart anymore. Okay? So that solution unfortunately isn't. So we have to be careful. Yes, you're thinking in terms of how to make this small. You've rectified this, but your solution has changed this outcomes here as well. And then comparing these two, you cannot conclude anything. Very well. Anyone has more suggestions? Maybe if you suggest something, I give you a full marks for PC 2130. No, I'm serious. Like, okay, so, like, I say this whimsically, right? But and I know that it's not possible in NUS. But I would like to do this because there are stories in other universities when a professor talks about an unsolved problem, gives a research level question at the beginning of the class, and says you can either choose to do the finals, go through all the assignments, or you can just think about this problem for the next few months and you can find a solution to it. And that's it. And in fact, one of the one very famous result in information theory, I can't remember what it's called, it's Feddel's inequality, was indeed solved this way. Like the professor just wrote an unsolved problem, sorry, it was Shannon's encoding theory, and then the professor just wrote a question and the student just solved it, and at the end of the semester they wrote a paper together. Now it's well known, right? It's used everywhere. I'd like to do this. I know that it's probably not allowed and frowned upon, and yeah, but why not?
What else?
Okay. You know what? It's too late for this, so let's postpone it to next week when I talk about it online. Yeah, I'll talk about it for the first half an hour, first 1 hour, let's say. But so I'll give you time to think about it for the next week. Over the weekends, your winters are all over. Every class is over, right? No? Alright, but still think about it. So the question, okay, so let me help you to set up the question. Here we've considered the case of one bomb. Okay, that's fine. Let's assume that the factory produces either all ducts or all live bombs. Okay, so of course you can imagine a setup where the factory produces a bomb. It could be live or duct, fixed bomb, live or duct, fixed bomb, live or duct. So those be independent, events, independent variables. But let me simplify. I guarantee you this condition that the factory, this particular factory, either has a very good manager or a very bad manager. And a good manager has excellent quality control, and once they have quality control everything, all the bombs will be live. But conversely, if the manager is bright, then all the bombs are ducts. Okay. Under this condition, then what happens is that, let's say you, as a tester, get a whole shipment of bombs from the factory. And let's say that n of them, but n is much larger than 1. And the question is, how do you verify all of them to be either live or ducts? Yeah, so if you test one, okay, so indeed, so Justin said, we already have an algorithm for one of them. So just pick one of them, stick it into the interferometer, and just run the test. But then you see that this, you have a 1/2 chance of blowing yourself up. The trick here is that and I'm claiming this, and I encourage you to invent this yourself. By using more of them at the same time, we should be able to lower this down, lower it down, increase this, and lower this. And when you keep all of these the same, then there'll be a way to do this. And which is also, if okay, so we haven't talked about the algorithm, but if you think about what I'm trying to say, the more you test it, the better, the safer it is for you, which is kind of ridiculous, right? The more you test it, then the safer you are. But I tell you that it will work. Okay, but I never told you what it is. Okay, maybe it's a go home and think about it. For now, let's break for 5 minutes, and then at 11, I guess the team